Hi there, Math 30-1. So I thought today I am going to go over this 2019 released exam. Rather than just having the answers here, how do we get them? So I'm going to go through the whole exam. So I don't know if this is going to take 2.5 hours or 2 hours or so. Hopefully it doesn't take that long. If it does, you can also just skip around trying to find the answer or question that you're looking for. Or you can sit here and just listen to me blubber on for a while. Hopefully it doesn't take what I need. You can see what time it is right now. Let's see how well we do. So this is a kind of a typical kind of question, this transformation one, where they have a point on a graph and they're just trying to figure out what happens when we do transformations to it. So like this one, sometimes it's a little bit trickier, like one of the ones from the previous release questions, you had to find the point first. It was the vertex of a quadratic, and then translate it. In this case, we just have a point on a graph, b to the x. Technically, I guess you could just find what b is, and then find a point on it, but let's not do that. What we're going to do is just going to apply transformations here. So based on what we have here, I can just rearrange this equation. I'll just minus the 3 over to the other side, and I can see that this piece here, that's going to be my h, because it's attached to the x. So remember in the form a bracket b x minus h, because this is literally touching the x, that's your h value. And the k value is kind of dangling there outside of the function. So my function in this case, don't get confused about this b and this b. My function is the b, it's the exponential of base b. Okay, so this plus 1 is moving it to the left. So you can write down like horizontal translation 1 left. I'm going to actually write the mapping down. So the mapping says that if I move left 1, I'm going to minus 1. And this negative 3, that's that k value, is telling me that I should be moving 3 down. Vertically 3 down, or 3 units down. So just putting in a point in here, so 3, 8. So this would be 3 minus 1, so that'd be 2. And this would be 8 minus 3, so that'd be 5. And there you go. Okay. Let me just highlight this part. So it makes sense when I look at this later. Why did Mr. Allen highlight that? Yeah. I'll try to post the PDF version of this online too. Okay. So my next one here, again, we've got another transformation question, but this time they just give us a bunch of ranges and domains. We just have to figure out what are these transformations over here? What do they actually do to the domain and range? Okay. So this part, that reflection, so this is a reflection, over or about the x-axis. This affects the y values, right? So it's going to flip the values of the y. So my y's are, I'll highlight it over here too. If my y values are negative 4 and 8, they're going to flip. So now it's going to be negative 8 and positive 4. So I can see that these two solutions would match, right? Now, before I maybe select one of those two answers, I probably want to make sure that this half is not also affecting the y values, but it's not, because this is a horizontal one. It's a horizontal stretch by a factor of 2, right, upon this. So I'm just going to write that down on the side here. Maybe I'll just write it on the top here. So this is a horizontal stretch. By a factor of 2 about the y-axis this time. Okay, so when you do horizontal ones, you're doing about the y-axis. So here's the y-axis, and I stretch it outwards on that point. So by a factor of 2, so that's very important that this is a factor of 2. So that means it's going to multiply all the x's by 2. So this would be 4 and 12, and I don't have any other 4 and 12s. So really, if I did that one first, I would have realized that this is my solution down here. Okay. And there we go. Okay. Well, The color coding kind of works nicely here. Let's see how this turns out. Oh, this is a fun one. Okay, so we're doing a transformation on a graph. We're trying to figure out what transformations we're doing. And then you should always read through the question. So you want to go from F. So you want to start here and you want to go to G. So you want to change from F to G. That's usually the way it's going to be. But then I read through these really quickly. I can see that there's these plus 10s here. And these plus 10s are going to move the graph vertically 10 units upwards. But that means any point that's on the x-axis are also going to move off the x-axis and move upwards, like after all the stretching is done. So seeing that these points, like these corresponding points to each other, this one and this one, that are still on the x-axis, it doesn't make sense to do any translations upwards. Right? And you notice that there's no horizontal translation in so many units. So I think we can get the same effect here by actually doing vertical and horizontal stretching about x and y axis. So we just have to figure out of these two that we have here, which one can do what we need to do. It looks like they're both going to do vertical stretch by a factor of 2. You can see how that works. So this point here was at 1, but now it's at 2. So you can see that's a factor of 2. This used to be 2 away, but now it's 4 away, so times by 2. Now this other one, we had to figure out the horizontal stretch. So it looks like it's gotten 2 times wider. So you can see that this was 3 boxes away, or like negative 15, times by 2 is negative 30. This was like 5, times by 2 is 10. Right? So there is a stretch factor of 2 about the y-axis here, right? Let me just do the last one here. Negative 30. So timesing by 2 to get to that point. So times by 2, horizontal stretch factor, that means we need a reciprocal of that to get our b value. So to get that horizontal stretch factor of 2, we got to have the 1 over 2. So this is horizontal stretch factor, horizontal stretch by a factor of 2. So times by 2 to get from here to here, right? Times by 2. Times by 2. Okay. I'll complete it up about the y-axis. Okay, there you go. So very important. Okay. So by a factor of 2, which gives us this little piece here. Okay. If there's a point on the graph, blah, 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 and then corresponding point after all of this. Okay, it's just another transformation question. The only trick about this one is that 3 should be factored out, right? So they call it a bad B, or whoever your tutor happens to be. I guess I would call it a bad H, but it doesn't make it, not a good alliteration there. So I'd factor out that 3, and I realize it's 4 units to the right. So I'm going to do a mapping notation here, just like I did before. Everything that's inside the function is going to affect all the x's. So I got this horizontal stretch factor by a factor of 1/3. So I'll put a 1/3 here. And it's left 4 units, so I'll go to minus 4 there. And then I got a vertical stretch factor of 1/2, and it's going down 1 unit. So that's what we have so far. And if I put this point in there, I think, is it what? -1, because 1/3 of -3 is -1 minus that, so that's -5, right? And then a half of this one, half of 4 is 2 minus 1 is 1. So it looks like it's C. Okay, just double check our answers here. Yeah, we're pretty good so far. Okay. Scroll, scroll, scroll. What do we have in here? Oh, invariant points. Okay, this is a very typical kind of question. This is very limited. It's just talking about a reflection. So remember that in a reflection, that when you do the mapping of that one, your x's and y's, they switch their spots. Right? So that means to be invariant, your point has to have the same x and y values so that that point does not move, right? Remember, we can have some points where some points overlap each other when they switch their spots, but those points literally had to move. So a point that doesn't move is actually invariant, so this point doesn't move. You can't have another point just kind of happenstance just replace the other point that was there before. But an easy way to figure out invariant points is just to figure out where the reflection or the stretch is happening. Like if it's happening over the line y is equal to x, then you draw that line y is equal to x, right? And that's where all the invariant points are going to be on, right? So here I can see that we have two invariant points. It doesn't cross up at the top there, so I'm going to have two. Now if it reflected over, say, the x-axis, I can see three of them because there's three dots there. If it reflected over the y-axis, I can see one there. There's one dot, one spot. So wherever axis it flips over, that's where the invariant points are. Yeah, let's keep on going. Restrictions. Okay, so remember when we're doing restrictions, like if I were to do like the reciprocal of this, or not, the inverse of this graph here, you switch all the x and y's, does that graph pass the vertical line test, right? After the fact, right? Of course, this is going to pass the vertical line test now, but afterwards, when you kind of tilt your head sideways, you can see it's going to make this kind of weird E shape. It's not going to pass the vertical line test. So you've got to figure out where to cut it. Now, you want this to always work. So the best way to always work is just find one of these max or these min points, I guess in this case the max one, and then pick this side that doesn't have any more up and downs to it. So this is just a quadratic. I'll just use this kind of sketch what this quadratic looks like. Now we don't know if it's opening up or down, but I'm just going to imagine that the point could be here. And let's just imagine it's opening down. Because it honestly doesn't matter, because what's really important is where this axis of symmetry is, this value here, because you just have to pick that and then pick one of the two sides. And based on our Math 20 knowledge and stuff that's on the board behind me, you can't see it because I'm on the beach right now, but that's your P and the Q, or the C and the D, because those are your transformations. It moves C units left or right, and then D units up or down. That moves this vertex to C and D, which moves the axis of symmetry to C. So you just had to pick one of those two sides, and they decided to pick the greater than side here for C. So that's the only one that actually works, or guarantees, because the other ones could work, but we don't know what A, B, and C, and D are. Or 0, it looks like 0 is not going to work on this one. Given the function. Oh yeah, so this one here, there's two ways to do this one. Like I was just saying with these inverses. If you take the inverse of a graph, remember the points switch. So if you're looking for, say, the y-intercept of the inverse, then the original graph, its x-intercept would be the same point, because they're going to switch the two spots. Like I said, like if I put example 0, 5, it's going to become 5, 0. So they're kind of switching on the axis it's on. Let me just erase it because that's not the example. So in reality, all I have to do is just find the x-intercept of this graph. I could find the inverse of this graph by taking the logs and stuff like that, but that's, you're going to see, we're eventually just going to have to do that anyway. Another way we could do it is just graph it. Just find out where does it cross the x-axis, and that's going to be the y-intercept later. If you want to do that, you can. But I'm going to go through all the steps. So here's my graph. To find the x-intercept, we make y equal to 0, right? So make y is equal to 0. Okay. And then we just start manipulating the formula, trying to get x by itself. The problem is it's in the exponent, but we start off by, say, add over the 16 here, dividing by 4. And I'll put that in that brackets. And now I need to get rid of this exponential, so this base here that we're trying to get rid of here. I need to get rid of this piece. So I'm going to take the log of both sides. I'm going to go log base 1/3 of both sides. So log base of 1/3 of this side as well. Oh, that x should be inside my, sorry, that should be inside my brackets here. Put that there. So this is going to cancel out, because that's the whole point of the inverse. Or, yeah, the inverse is supposed to cancel each other out. So when they cancel each other out, it becomes an x. And then this over here is all I need to calculate. So I'm just going to pull out my calculator. I just got my calculator here at my beach. I'm surprised I brought my calculator with me out to the beach. Now, if you have the calculator base button, use it. If not, remember you can type the same thing by going log 4 divided by log 1/3. That's what I have to do in my calculator, because I turned off that functionality. Now you can see it's negative 1.26. So it's approximately negative 1.26. I think it says approximately. To the nearest hundredth, yeah. There you go. Now you could have just found the inverse, which would involve the same steps as what we did here, like minus, or add over the 16, divide by 4, and take the log of both sides. But you just have a y left in your equation. That's fine. Okay, this one here, we're just trying to find the value of theta. If you know that log base 2k is a half, and then we just want to find out, based on this, if I knew what k was, I can probably find out what theta was. So I'm going to use this first part to find out what k is. So to get rid of that, I'm going to go 2 to the power of both sides, because you want to get rid of the log this time, so you just have to do the inverse. So 2 to the power of a half. I'm going to cross this off. So I'm going to k. So k is 2 to the half, which technically is the square root of 2. Okay. So now we know what k is. Okay. Put that right there. Okay. Then I'm going to go over here and put the k into that equation. So cosecant theta is equal to root 2. Okay. So now, remember that what cosecant is. Remember, you just go to your formula sheet. Cosecant is the same as 1 over sine. Okay. So that means I'm just going to take the reciprocal of this one and flip it over. And I'm going to go 1 over root 2. Remember, that's the same thing as root 2 over 2. If you want to rationalize that, you can. So looking at this, I know that theta is sine, okay, but the reference angle for this is going to be 45 degrees, because that's the root 2 over 2 on our unit circle. But according to our unit circle, sine is positive. You can see there's a positive here. You don't really see it, but it's positive, so very important. It's positive in the first quadrant and the second quadrant, but not the bottom 2 quadrants. Remember, it's the y value. So the y values are positive at the top half. But this is limiting us just to this second quadrant here. So we're trying to find this angle going around here. Okay, so I know the reference angle is 45. I'll put a 45 degrees in here. So this is going to be 180 minus 45. So it's going to be 135. And there's our answer, 135. So just put a box around it. I'll put a box around it over there. That's 135. Cool. Okay. Now to verify, you can put it back in there, find the k value, and then put the k value back in there and see if that actually works. It should work out. Okay, now this kind of question shows up on all diploma exams. Lots of our practice questions have this as well. This is a very typical question. Now, one way to solve this is to find out what x and y are, plug them into the bottom equation, and then calculate what's that over there. But you'll have to find out what m is well, x, y, and m. Do all the calculations. Plug it into the second part, like the second part over here, and then see if it matches any one of these. It seems like a lot of work, but it's not impossible. Like, there are 2 ways. Maybe I'll just do both ways. I'll show you what it looks like. Like, I think the first way, which I'm going to do, is the way they want you to do it. So we have this number here, this 100, and then we have these other two numbers here, all base 3, so that's good. We just have to figure out how do I make 100 out of 5s and 4s. Okay, so I can make 100 out of 5s and 4s by going 5 times 5 times 4. Okay, then I just have to think, okay, how do I make m to the 4 out of m squareds? Okay, so I can make that by going m squared times m squared. Okay, so you could just say that's 5 squared if you want to, and that's m squared squared. Kind of like it this way though. So because our log laws say that when I'm multiplying things inside of logs, I can separate them to addition. Well, usually we go the other way, where we kind of bring them together. But we can always separate them. So this is log 5 plus log 5 plus log 4 plus log, this is running out of space here, log m squared, and then log m squared. So wherever I see like a log 3 base 5, or log base 5, 3, I can replace those with 3y. So I'll go 3y. 3y plus 3y. Wherever I see a log base 3, 4, I see a 2x. And wherever I see a log blah, 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 I put a 6 there. Okay? So we get 6y plus 2x plus 12. And you can see that's going to be that one. Now the other way to do this question, or it's just solve for the individual pieces here. So if I want to solve for what y is, and solve for what x is, and then solve for what m is, that's a bit trickier. And then I could put those into the equation. So literally what I can do is I can type out log base 3. Well, but I have to find out what m is first. So let's find what m is. Okay, so log base 3, m squared is equal to 6. So I'm going to solve this. So I'm going to, let's take the 2 and drop it down. Now this is, I probably wouldn't do it this way, but it is possible. Nice, and you can solve for m now. So m, taking the base 3 on both sides, or 3 to the power on both sides here, I would get 27. Now you can just double check that. Here's a log base 3 of 27 squared, 6. Yeah, so I get 6 there. Okay, so now I know m. I can plug that back into this equation over here. So log base 3 of 127 to the power 4. Okay, so log, I'm going to get probably a decimal here, but that's okay with me. I'll have brackets to deal with here. Okay, so approximately 7.725. Then once you know m, all right, or you don't need to know m anymore, you just have to figure out what x and y are. So y, based on the formula, is just log base 3, 5, all divided by 3. You just divide the 3 over. And x is a log base 3 of 4, all divided by 2. You just go back into the equation now, and if you know x and y, so you put them into the equation, figure out which one actually matches up. Seems like a lot more work, but it's possible. Meh. It's up to you. I'd rather do the left side here. Okay. All right, so this is a fun one, because they're trying to combine this together as a single logarithmic expression here, but there's this dangling 4 here. We're trying to figure out, okay, how do I combine a constant number into a log? Right. So we can easily combine the first two. First of all, because our exponent law says that we need to, or log laws say we can't have these coefficients in them if I'm going to try to add them. I'm going to move that up into there. So let's just get rid of that for now. Now when you raise it up there, you're raising the a and the c together to the power of 4. So you can write them separately. A to the power of 4, c to the power of 4. Right? And then I can combine those together. Okay. So we get a to the power of 4, b, c to the power of 4. I like to write things in alphabetical order. You kind of see they didn't, but you probably should. But now with the last step is try to figure out how do we get these things together. Now because it's not a log, I can't just say divide by 4. It's not a. Right? I can only combine it if it has the log. So we have to go back and we have to think, okay, here, I don't want to change this number, but I can change the way it looks. So I can put a 1 here, like 4 times 1 is still just 4. But what is 1? What is always 1 in terms of log? Well, log base any number to the same number. We're going to pick a because they used a here. So I want to make sure the bases match so I can combine them together. But log base a of a, 4 of 4, 5 of 5, whatever, they're all going to be just equal to 1. So I can add any log I want in there because it's just 1. Now using the same rule, I can bring this exponent up over there. If you want to, you can bring the negative with it. Usually I don't. Just a little bit more confusing if you do. So I'll leave the negative behind. It'll be a to the 4. Okay? Now there's the minus rule, says you divide the 2. Oh, I forgot to do that. It's got to be inside the brackets here. Okay, so I'll extend that bracket down a little bit more. And then I can see that we can cross off the a to the 4s. I'm left with b and c4. So let's see, right? Is that a hard question? 59% got that one right. This is supposed to be a pretty hard question. Okay. Cool. Let's go down here. The value of b, so this passes through 0, 0, or passes through 2. Oh, this is a kind of like a, what do you call, system of equations. It may not be, based on some of the numbers. Maybe some of the numbers will just help us out. They'll just kind of work themselves out, which hopefully it does. Hopefully. I don't know if it does. So maybe one of these points can help us find the b or the c, and then we can use that to find the rest of them. Because it looks like I have to find b first. Okay. So we do have 2 unknowns. We've got b and c here. But we have 2 points, which is going to be nice, because that's usually how these kind of questions work out. So I'm going to take one of the points. I'm going to put the 0, 0 in first. So what it says is that if I put a 0 into this equation, I need to get a 0 out. Right? So this is the 0, 0 point. Right? The other point over here says that if I put a 3 over 2 in, I get a half out. Okay, so I would get half out if I put a 3 over 2 into this equation. So I'll start that one. But then I just have to figure out which of these 2 would be the easiest to solve. I think the other one. What do I have here? Let's see. Or maybe I don't know which is going to be easier to solve, but we'll see. This looks a little bit easier. It doesn't have any 3 over 2s and a half. It has a 0. Maybe this could help us out. I think maybe it will. I see what it is. Okay, so what we're going to do is we're going to just see if we can solve for C or solve for B. But they're both inside the logs in their respective spots there. One's the base and one's the inside. So I'm going to have to get rid of this log. It's a base B log, right? So I'm going to use a base B exponential. Kind of weird, but I'll do it. So I'll go B to the 0, and then B to the log base BC. So that's going to cancel out the b's here, but also b to the 0 turns into a 1. So c is 1. Well, that's good. Then I can go over here and just put in the 1 that we just found. So I'll just highlight that so I don't forget where that came from. So here. And then I'll go over here and put in that spot. So plus 1. So that would be 2.5 or 5 over 2. No, that's not right. Yeah, 5 over 2. I don't know what I was thinking. So I'll just put that in there. Now we're just going to try to solve for b now. Okay, so just like over here, I'm going to use a base b exponential to get that b out of this spot here. So b to the half is equal to, and then we do the same thing we did last time. So this. Okay, then we cross off those. And we get 5 over 2 is equal to b to the half. And now we just have to try to get rid of the b to the half. So you could take a half root if you wanted to. You could also just square both sides. That's essentially what a half root does, because if you square both sides, the power to the power rule says that turns to b to the 1. And then this squares out to be 25 over 4. So what was that? 25 over 4, 6.25 fits really nicely into our 4 boxes there. It's fun. Yeah, that's a pretty good question. It's an interesting question. Okay, given that this is equal to that, and this is a weird one. So interesting. What are you trying to find here? Oh, kind of a substitution slash system of equations again. It really doesn't matter what a is. Actually, yeah, it doesn't matter what a is, because you'll see that we'll just have a log a of a, which kind of cancels out again. But first thing we're going to do here is you could just plug this into here and then use your log laws, but you can also just combine these. Because they both have the same basis, we can minus our exponents. So we can minus our exponents. It's kind of like the idea that they put these in brackets. It kind of helps us out. You can see that this will simplify to a x minus 2x plus 6. So it'll be a to the negative x plus 6. Okay. Now we have that. What I'm going to do is I'm going to take this, because that's equal to y, I'm going to put that into the y spot up here. Okay, so I'm going to go log a bracket a to the power of negative x plus 6. And that's equal to x. Okay? Now, because of this log a of a, I can cross those off, because they're inverses of each other, and then we're left with this. Cool. All right. Rearrange this equation. Add that over that side. You get 2x divided by 2. And you get 3. Cool. Seems like I get 10a. Yeah. Not too bad. A lot of people got that one right. Seems like a bit hard to read question. Joe here invests a bunch of money, compounded annually. I do like the fact that it's annual interest annually, so I don't have to worry about like the t over p stuff. So this means that p is equal to 1, okay, because it's compounded annually. Plus, I don't have to deal with like dividing by 2 or something, because it's annual interest as well. We're trying to find the per year interest. It's 12 years later. His value has doubled, so he has $9,000 after 12 years. So we're going to set up the equation here. Our typical formula that says y is equal to ABT over P. We're just going to fill in all the pieces that we know. So we know that our initial amount, 4,500, I'll put that there. My B is what we're trying to find. We'll see why that is in a second, or how we're going to use that in a second. Our T is 12, and our P is 1. So I'll put a 1 there, and I'll put a 9,000 on that side. Okay, so we start rearranging this. So if I divide over the 4,500 first, I get 2. Okay, so this is a much easier equation to solve. So I just have to solve for B. Now, a couple of different ways to solve for B here. You could take a 12th root. I guess so. You can take the log of both sides. Lots of different things you could do. I would just probably take the 12th root here. 2 to the power of 1 over 2. Okay. So if I do the 12th root or something along those lines, you're going to get 1.059463. Okay. Now that's not the answer. Because remember, when we calculate this stuff, when we do this annual interest stuff, we always go 1 plus our interest, right? That's what it ends up being. So the 1 stands for the 100%. and the other decimal is actually the actual interest here. So we'd have to minus over this 1 here, and you get 0.059463. You probably think, yeah, because I want to do the nearest hundredth. Like, why did Mr. Allen have all these decimal places? Because he needs it to change this into percentage. So I get 5.95%. Okay. So you have to watch out for these kind of questions. Probably the most common answer for this one, because it was one of the harder ones, about 45%, is most people probably put down 1.06. Right? They're not going to give you part marks. Let's mark it wrong. Right? You have to be very careful what they're actually asking for. Okay, so it's 5.95% interest. 1% interest would be really bad. In order to factor this polynomial, so you determine that potential 0 was 3. That's good, because remember our potential zeros could be plus or minus 1, 2, 3, and 6. Good potential zeros. He wrote that the polynomial has a product of a linear factor and a quadratic. So he did the synthetic division here, it looks like. He just wants to figure out what's the quotient going to be. Okay, so if my 0 is 3, I know that this is going to be x minus 3, right? That's what we know so far. So because of that, I know this. It's always the opposite. Our factors are in zeros are switched. So we can cross off a few of these answers. I'm going to cross off this one. I'm going to cross off this one because this negative 3 here. Okay. But now I just have to figure out what happens when I synthetically divide. So depending on who teaches synthetic division, in our course, we just use the zeros to do this because then we can add rather than subtract. Just make sure that we have everything. So we got 3, 2, 1, 0. So we got all the numbers. And I want this to be 0. Hopefully it is 0 because they determined it was one of the factors. So we drop the first one down. We multiply. We add. We multiply. We add. I messed up here too. We multiply and then we add. So we get 0. So what's left over here is this stuff here. And you can see that 3 matches up already. It's a given. But then we have 7 and 2. So we look for B here. So we want 7. So the only one that matches up would be B. Okay. Cool. Now this one, I just don't like this question because they give us a lot of information here we don't need. The only thing that we need in this question is that the fact that it has a minimum value of negative 66, right? So based on just that, and that we know that odd, because the possible degree here, odd degrees don't have minimum values. They have relative mins, but they don't have absolute mins. If they don't put the word like relative in there, we assume that this is an absolute minimum value. So like odd graphs, like degree of 5, positive or negative, like if it was positive, it would look like this, right? And if it was negative, it would look like this. I don't know exactly what it would look like, but they go up forever and down forever. So there's no minimum values here. So I can just cross these off, right? There are no minimums. So the only ones I have to choose from now are 4, the degree of 4. They have like, they both open up or they both open down. We just have to remember that positive means that the graph opens upwards, and negative means that the graph opens downwards. So if we want a minimum value, we need values on the bottom, right? So the only one that this could be is A. For some reason, a lot of people got that one wrong, 16%. We didn't need this. I didn't even look at this other stuff here to figure this question out. Just didn't know that was a minimum value. That was it. All this useless information. You can draw it out now if you want to. You can draw it out what it looks like. Okay, so this graph here, okay, this is a fun one. So this one wants us to determine 2 things. If I go down here, A and E. So they want us to figure out these 2 pieces of this graph. Now, E is really easy. right? If I put a bunch of zeros in all these x spots, the only thing left over is e, because it'd be 0 plus 0 plus 0 plus 0 plus e. So let me just change my color coding here. So if that's all that's left over after I put zeros in the x spot, that means that's my y-intercept. So this is all, if my constant value, if there's no x on it, is always my y-intercept. If it has an x on it, and that's the last one, that means my y-intercept is 0. But because the y-intercept is 8 here, that means e has to be 8. That's the only thing we have. It's just right here. I'll just highlight it, right? It's got to be 8. Okay, now the other part's a little bit tricky. To figure out what a is, we're going to have to start creating this equation. So we have two zeros, but they have a multiplicity of 2, right? They have a multiplicity of 2. That means that 0, I'll put that 0 in. So they say this 0 here, -1 is plus 1, is squared. And this one has a -2, but it's also squared, right? Now at this point, remember what I had to do. If I put zeros in there, I should get 8, right? That's what I should get. But 1 squared times 2, -2 squared, doesn't matter if it's -2 or +2. So that's 1 times 4, I get 4. So if I put a 0 in here, actually I'll put it down here. If I put a 0 in, I need to get an 8 out. That's what that point is saying. So I need to get an 8 out if I put a 0 in here. But I don't. 1 squared, -2 squared, this is equal to 4. So something has to be in this gap here to make this work. Some a value has to be used to make sure that this works. So it just looks like a has got to be 2. Now this a, oh, geez, that was bad. I'm supposed to highlight that, sorry. This a is the same as this a that's up here. Now, if I were to multiply this out now, that a would just end up being in the front of all the x's. So we have a 2. It's positive, which is nice because it is opening upwards. I don't know if that mentioned it anywhere, but it is positive. It says up here it could be an integer. But so DE could have been negative, but it wasn't. Okay, cool. This is a good one too. So what do we have to do? So invariant points and domain. Okay. So remember that when I take the square root, so look at this graph up here. So this is saying this is equal to f of x. And here's f of x. So what this is actually saying is you're taking the square root, the y values are just the square root of the y values. The old graph, of course. So this is f of x here. I just want to take the square root of my y values. But the y values down here, this is the square root, this would be the square root of negative numbers. And that's not happy in the real world, right? So I can't do that with these values down here. So these parts of the graph just kind of disappear. And all I'm left with is all these positive ones, but on the outside edges here. So I'm only left with parts of the graph that go this way, and part of the graph goes that way, right? So I have this big gap in the middle of my graph, because the negative part is in that middle part, so I lose it. Now, if it was upside down, the negative part would be on the outside edges, and then the positive part in the middle. But since I'm losing the negative part in the middle, I know I'm going to have to be using the OR statement here, so I'm going to cross these ones off. So I know it has to be one of those two. But now we have to remember, how do I get invariant points? If this is my mapping, essentially this is my mapping. I'm just taking just my y values, but I'm leaving my x values the same. Okay, so I'm going to go x, the square root of y. Now, if I have a 1 in there, what's the square root of 1? Well, it's 1. So that's invariant. Also, if I have a 0 in there, what's the square root of 0? Well, it's 0. So invariant. So my invariant points happen when my y values are equal to 1 and 0. So I had to look at my graph and say, okay, so when do my y values equal 1, 0? So I have two lines here. This line is y is equal to 0. And then there's no scale here. Just imagine the lines right here or something. There's another line, y is equal to 1. So I have 1, 2, 3, 4 points here that cross that point. So there'll be 4 points with y1 and y0. So, okay, cool. Okay, our vertical asymptote here. Oh, this is a good one. Okay, so vertical asymptote, remember, is something to do with the non-permissible values. So we got to figure out what the non-permissible values are. So I'm going to have to factor this out. Okay, so let's factor the tops and the bottom of it. Or it's just the bottom right now. Let's start with there. So I'm going to factor the bottom. So you always look for a GCF. I can't factor out the 4 or 2s or anything. So I'm going to go 2 times negative 18. So I'll write this on this. I don't know where I'm going to write this. I'm going to write this up here. So I need numbers that multiply out to negative 72, but add to negative 1. So that'll be 9 and 8. 9 and 8. I know I said that wrong. But negative 9, positive 8. Okay, and depending on what method you pick, I'm just going to pick this method. Okay, so down here, I'm not going to write exactly what this is. Remember, this is Joe's method, so I'm going to actually highlight this piece here, and that's what I'm doing up here. Okay, and I'm going to have to factor the other one as well. But the other one I could factor easier. So you reduce them out. So this side over here doesn't reduce. I'll just leave that alone. But this side I could divide both by 4. Look at that. Now the top factors really nicely because it's just x squared. It's just x times x. So I get 5 and 2, negative 5, positive 2. Okay, so now I look at this and I say I have two non-permissible values. I have negative 2 and 9 over 4. But I said that my non-permissible values are my asymptotes. But only the ones that don't cross off. So that's this one here, right? The one that crosses off becomes a point of discontinuity. The one that does cross off is my point of discontinuity. The other one is my asymptote. Okay? So my asymptote is going to be 9 over 4. 2.25. Yep. Good. Now a side note, my other asymptotes, just for the fun of it, this is my vertical asymptote, because this is what we're looking for. We're looking for the vertical asymptote here. My horizontal asymptote, just for the fun of it, is equal to y is equal to 1/2, or 1/4, sorry, 0.25. So we can find that by dividing our leading coefficients if the degrees are the same. Up here you can see that the degrees are the same, so I just took those two numbers and divided them. My point of discontinuity, and let's keep on going here, my pod is at -2, comma, remember it's a point. So the harder part is to find out what the x or the y value is going to be. So the x value is easy, it's -2. But I'm going to put the -2 back into the equation. But remember, it's a simplified one. So I'm back in here where it says x minus 5 and 4x minus 9. And get 7 over 17. All right. That's just a side note. You didn't need that. That's okay. Oh yeah, this is an ugly question. 14. Is it a hard question? Yeah, 50% got this wrong. Okay. So the reason this question is ugly because it's two parts. If you got one part wrong, you got the other part wrong as well. Now what we know, what we need to do, because later on down here, we're going to do a composition. We're going to put one function, specifically we're going to put f into g. All right, so we got to find out what f is. Okay, here's f. Okay, that's good. So I know what f is, so I'm going to put that here. So I'm going to put f into g. Now the problem with g is not complete. We're missing a bunch of letters up here, A, B, and C. If I knew what those were, then I can actually complete this and actually find my answer. So I've got to figure out what the A, the B, and the C are. Okay. So to find out each of the pieces, which is kind of nice, this is what we call transformation form. We have this kind of dangling piece out here. That is just my horizontal asymptote. Right? That piece, that C that's kind of out there, that's like my K value. It's kind of, they wrote it in the ABC way to try to confuse us, but really what this is, it's in the A, the H, and the K way. So C and the K match up. So I'm going to move the graph up 1 unit. That's going to be my horizontal asymptote. And then my other asymptote, this one here, that's my H value, or my B value, I should say. Okay? So those two things there, they're my H and my K. So I can write my equation out so far where I have A, which we don't know yet, but I do know that this is going to be minus 6 because it's moved to the right 6 units, and then up 1 unit. So that's what we have so far. And actually, this is all we need to solve this question, but let's find out what the A is. And we can use this other point here to help us find out what this A value is. Okay? So we're going to put in this point 7, 0 into this equation and find out what A is. So if I put a 7 into the equation, I need to get 0 out. So let's rearrange this. So 7 minus, that's A, because it's just divided by 1, plus 1. So A is negative 1. Okay. So now we know what G is. So this is G. I'm going to write G of X down here. So G of X. It's negative 1 over X minus 6 plus 1. Okay. So now what we're going to do is we're going to put f of x into that equation. So we're going to put this here, because it used to be where the x used to be here. We're going to put that in all the x spots here. Okay. So I'm going to go negative 1 divided by x squared plus 3x minus 4. That's where the x was. But there's still minus 6 here from before. And I'm going to just simplify the bottom down. And now we got to figure out what are my restrictions. My restrictions are what makes the bottom equal to 0. So really, I didn't need to know this 1 or the negative 1. I just need to know what's on the bottom of this thing. So I'm going to factor it out. Negative 10, so that'd be 5 and 2 again. So positive 5 this time. Negative. And then we're just going to look at these two things in the bottom now. So this part and this part, that matches up with D here. So there we go. All right, we got it right? Yeah, we got that one right. Cool. Hard question, really long question. All right, so now we're question 15. Yeah, cool. The carousel has a diameter of 22. Diameter. Now this is always, they always do this. The word diameter, we want the radius. So just make sure you divide this by 2 here. And we actually have 11 meters for my radius. Okay, so just make sure you're always using your radius, not your diameter. So the central angle formed when an adult travels, let's write my radius down here. 11 meters. Yeah, sit on the outside edge. Is the central angle formed when the adult travels 10 meters around the thing to the nearest degree is, and I'm just going to guess it's the 52. That's my guess. I'm going to guess it's 52. Or should I guess it's 30? I think it's 50-ish. It's not quite 60. I'm going to guess it's 50. That's my guess. Estimation. You can actually kind of literally draw what this looks like here. So we have a radius of 11 meters. If I draw something that looks similar to about 10 meters here to kind of scale-ish, I'm looking for this angle. Now, the thing about the formula is that the formula theta is equal to A over R. This needs to be in radians, or you get radians out. One of the two. So in this very specific case, when I do this, and I go 10 divided by 11, meters and meters, the meters cancel out here, I'm going to get this in radians. 10 divided by 11. So this is going to be 0.9. So they obviously helped us out because this doesn't make any sense. There's no answer for this one. Remember, this is in radians. Technically no units. You can see that the meters cancel out. So I need to change this, approximately, into degrees. So we set up our ratio. We put this number above the right side here. And then we're just trying to find this question mark. So we're going to cross multiply and divide here. So cross multiply, divide. Times by 180, divide by pi. So actually literally divide by pi. Hey, look, that's that 52 degrees that I thought it was going to be. Kind of looked like it when I drew it. It could be at 52 or 63. But that's okay. Cool. Just remember this. Radians. Radians. So highlight that. More radians. Okay. The additionals change. So here it looks like they're minuses. They want to know what happens to this point if you minus 270 degrees from it, or 3 pi over 2, which is about 270 degrees. So what if I do this to this angle? 270 degrees, right? So first of all, I've got to figure out what this angle is. Right? There's lots of different ways to find this angle. You can use your trig ratios. You can use your knowledge of the unit circle. I'm going to use the knowledge of my unit circle here. This definitely looks like it's 30 degrees. There we go. Again, 30 degrees. Or if you want to leave it in, pi over 6. Okay. Just based on just how it's drawn. They usually try to draw it pretty accurately here, but the shortest side is the y, the longer side is the x, so it has to be 30 degrees. Okay, so now if I take this and I minus 270 from it, where does that land? So I'm just going to do that right now. So negative 240. So they did this so that you can deal with negative numbers, but remember you can always just change it to a coterminal angle by adding 360. So if you did that, it would end up being 120. But either way, your angle is going to end up right in here. Right there. So this would be negative 240 degrees. So you're minusing the 270. And you also see there's like a 90 degree left in there. Like that's 90 degrees in there. But that's beside the point. So now if I know that, I can figure out what this point is, because this forms a 60 degree reference angle. So this angle in here is 60 degrees. Right? So that means this kind of flips. So my x is negative, because I'm in this quadrant. So that's going to be 1/2. My y is positive. All right? Yeah, there we go. 16b. That was a hard question. Yeah, most people got that one right. But this, I think, this 2019 exam was actually pretty easy. A lot of people got this one right. But the next question, this is, they say this is the hardest one. Because it's kind of confusing. But in reality, they're just asking you to solve for A. But the key for this, okay, is that this is on the unit circle. Okay? So let's draw this out. A, negative 2a, so somewhere down here. A, negative 2a. I don't think that really helps us out. But what I know, because this is on the unit circle, it is a, negative 2a, is that this is 1, right? Because it's on the unit circle. My hypotenuse is 1. So if I were to draw a triangle here, a and negative 2a, it's got to satisfy that. It's got to be on the unit circle. So I can set up a squared plus negative 2a squared. That just has to equal 1 squared because it's on the unit circle. So let's do some math here. This is going to end up being 4a, right? Yeah, plus 4a squared is equal to 1. So this is technically 5a squared is equal to 1. That means a squared is equal to 1/5. So you just divide the 5 over, and then you take the square root of both sides. Okay, so the square root of 1/5. Remember, that's just the square root of the top, square root of the bottom. It's like an exponent, so you just apply it to the top and bottom. So the square root of 1 is 1. And this is the square root of 5. So 1 and 5. The numerical response ones are always very hard. But yeah, 1, 5 is the answer for this one. Unit circle. Remember that. Okay, so secant is equal to that. What's the value of cosecant? Well, I really don't like these reciprocals. So what I'm going to do is I'm going to change this one into cosine, because that's what cosecant represents. But remember, that's just the reciprocal, so this turns into a 12 over 13. Now, what I know about this is that it lands in the 4th quadrant, so quadrant 4. So somewhere in this quadrant, I think somewhere right about here, I have a triangle. I don't know how big it is. Actually, I kind of do know how big it is. It could be scaled up or down, really. But according to cosine, my adjacent is 12 and my hypotenuse is 13. Cool. Now, what's very important is that my y value is going to be negative. Right? So that, I'm just going to cross off these ones because those are not negative, because cosecant represents sine. Right? So if I can find sine theta, I can find out what cosecant is by flipping it over. Actually, I already know the answer now, because I've got to flip it over. It's got to be this one here. But let's just double check. So Pythagorean theorem says, yeah, this is equal to 5. Let's just use the Pythagorean theorem here. So I just put 13 squared minus 12 squared is equal to question mark squared. We'll call that the y value. So 25 is equal to the y value squared. Y is equal to 5. Plus or minus 5. But I know it's going down. So it's negative 5. So I'm actually going to put the plus and minus here. An even root gives us a positive or a negative. Okay. Key is that that's a negative there. Oh, I could use a different highlighter here. Okay. Now sine is opposite over hypotenuse, and then we flip it over to get that one. So you get 13 over 5. 13 over negative 5. Okay, that's a fun one. Exact value of a plus b, and they're giving us a and b here. Yeah, this point's on a and this point's on b. Okay, so I'm going to draw both of these points out here. So alpha is, well, a if you want to, is a negative 7, negative 4. Right about there. That's negative 7, negative 4. So that gives me negative 7, negative 4. Okay, that might be just enough. I don't know if I need to find the hypotenuse enough. I'll see if we need to later on. Beta is at 2, negative 1. So right about there. 2, negative 1. Cool. And again, I don't know if I need to find the hypotenuse here. There's no square roots or anything, so I'm assuming I'm okay here. Okay, so what I know so far, if you want to, you can just fill out some of these. this is probably going to show up useful here. Opposite of our hypotenuse for this one is -4 over -7. So this is 4 over 7 for tan. And for tan beta is going to be -1 over 2. Okay, so this one's positive 4 over 7, negative. Okay, the reason that's important is because according to our trig identity, for alpha plus beta, pull up my trig identity sheet. Okay, I'm going to leave the beach here for a second. Okay, what it says is that tan alpha plus beta is equal to tan alpha plus tan beta, all over 1 minus tan alpha tan beta. Okay, so now what we can do is wherever we see a tan alpha, here's tan alpha, I can put that in those two spots. And wherever I see a tan beta, here's tan beta right here, I can put it into these two spots. So tan alpha is 4 over 7 plus a -1 over 2. Okay, I'll just put that there. 1 minus 4 over 7 times -1 over 2. Okay, so in reality, you could just punch this in your calculator, see which one it matches at this point. But if you want to go through all the steps, like if this was a written response question, they might ask us to show more of your knowledge about this. So I'm going to go on the top here, might as well just minus a half, and just go math enter here. Ooh. So I get 1 over 7, 1 over 14 here. So double check that now. Doesn't seem to. Right. Yeah, 1 over 14 here. Okay, and on the bottom, that's just me adding the two numbers on the top. And the bottom, I'm going to go 1 minus 4 over 7 times -1/2. So that's 9 over 7. Okay, since we're divided by a fraction, this would be the same thing as 1 over 14 times 7 over 9. So that's like 7 over 14 times 9. There's other ways to simplify this down, but you could do it this way. You could have reduced the 7 and the 14 and got a half there, but this ends up being 1 over 18. It looks like it's a positive number too. Did it end up being negative? So 18 is a mean A. Perfect. Okay. Oh, this is a weird question. So we have these two graphs, or two carousels, two Ferris wheels here. Now, some key things about this: they both require 40 seconds to complete one revolution, because the period is the same for both of these graphs. When I do the b is equal to 2 pi over b or whatever, or 2 pi over the period, sorry. It's just going to be the same for both. Same for both. You can actually calculate it if you want to. You can do 2 pi over 40 or 360, over, depends on which units you're using. But the b is the same for both, right? So and down here, we're just thinking what must be different. So if the b is the same for both, I can cross off anything that has a b in it. So I'll cross this one off and I'll cross this one off. So now we just have to figure out, is the A or the D, or the A or the C, because it looks like the D is different. And that makes sense because the D is our midline, right? Our midline is the line that kind of cuts it down the middle. So there's my midline there, and here's my midline here. So these both have different midlines. If I imagine my axis was like here or something, this distance is definitely different than this distance. This is like my D value here. So D has to be different, right? For sure. Now, my only thing now is to figure out is it the A or the C? So let's look at the A. Now remember, A is the amplitude. So it's measured from the midline to the max, midline to the min. My amplitude is going to be, let me just highlight this in a different color here. My amplitude is going to be this distance here, right? That distance there versus this distance and this distance. So this purple line, those are my A's, right? They have to be different because they're different sizes. Now, phase shift is just where they start, essentially, because the periods are the same. They're not going to go out of phase eventually, but if they both start at the bottom of the carousel, they both start at the bottom, then why would they have a different phase shift? So it's my A value and my D value. Now, for the phase shift part, I can show you what that looks like here. Imagine this is the where they take off. So for the bigger one, it's going to look like this. That's the bigger one, right? So there's my full period. There's 40 seconds there. It goes up to a max height. I don't know what it says here. 25 or... I measured to the wrong spot here, but let's say about 25 or so. All right, but you have to remember this down here is like -3. And then if I do it for my other graph, it has the same period, but it's not going to be as high, so it's only going to go to about there and then back down, right? So here's 10, right? So they have different amplitudes, they have different midlines, and they're in phase with each other. They start in the same spot. So why would their C's be different? Okay, let's go down more. We're on a roll. It's only an hour so far. But I do teach this course, so that's a problem. Oh, this is a good question because it involves graphing. So I'm going to put my graphing calculator here. So the average temperature of a particular Alberta town is represented by blah. T is the time in months after January 1, so the first day. The minimum number of months to the nearest tenth of a month to take for the average temperature to rise from 5 to 15 is how many months? Time in months. So, okay, so let's graph this out. I'm going to type it in on this side over here. I'll just, once I type it in, I'll bring my calculator over. So let's see what this graph looks like. So 15.8 sine pi. So that's giving us a clue about what units to use here. Where's the pi button? I can never remember this because I don't use this calculator that often. Oh, it's right there. Okay, pi over 6 bracket x. So you can't use t's, you have to use x's here. Bracket, bracket, plus 5. Okay, here we go. Oh, I missed the plus 5. There's the plus 5 there. I think that's right. Let me just double check. Always double check your enough brackets. Sweet. Okay. So I'm going to go here. I'm going to go, because I'm in degrees right now, I'm going to change that. So I'm going to go to my modes, change it to radians. Because of the pi, indicates that this is going to be in degrees. Then I'm going to go zoom, trig to start off with. Okay, but that's not the proper window. So to get the proper window, we're going to have to figure out what is the period, so I can figure out what is my range going to have to be. So let's find out what the period is first. Right? So my period is going to be 2 pi divided by the b value. Pi over 6. So I'll go through all the steps here. 6 over pi, because you have to calculate across it. 12. Okay, so now I know the period should be 12. So I'm going to go over here. I'm going to go my window. I'm going to start at 0 and go up to 12. Okay, so I'm going to graph that. So there's my graph so far. But I also need to know what the min and the max are, so I have some, so I can see the top and the bottom of the graph. I probably don't need to, but I'm going to do it anyway. So my max value is going to be 5 plus the amplitude, right? Remember, this is going to be my d plus my amplitude. So that's going to be 20.8. And my min value is going to be 5 minus my amplitude, which ends up being negative 10, right? Yeah, negative 10.8. Okay, so 20.8, 10.8. So I got my window here, blup, blup, blup. Negative, this is my min, so negative 10.8. You can give yourself wiggle room here too if you want to, and then go up to 20.8. Ah, look at that. That's a very nice looking graph. Okay, so it looks pretty good to me. Let's see what we have. So we're trying to find the minimum number of months to the nearest tenth of a month it takes for the graph to rise from 5 degrees Celsius to 10 degrees Celsius. So let's find 5 degrees Celsius. I'm going to go to my calculator. Put a 5 in here. Graph. So right there, if I do the intersection point, I found the wrong one, so I'll go back here. Second trace 5. Enter, enter, and I'm going to guess over here. So actually, I probably should move my decimal because this is in radians. It's hard to guess in radians. About 3. Actually, exactly 3. That's kind of nice. All right, so I'm going to write that down. So the 5 degrees happens at 3 months. So I'm going to write that down somewhere. 5 degrees happens at 3 months. Okay? Months. Now I just have to find the 15 degrees months. So let's go back here. So I can just change this to 15. So now the line's a little bit higher. And go second trace, intersect, enter, enter. I probably should guess over here somewhere. 4.3 months. Okay, so I'll put that over here. 4.3 months. So these are all off the graph here. The difference between the two is 1.3 months. So it'd be A. Okay, so let me just let me do that. Where did that go? Oh, it popped up down there. Okay, so that's not the most ideal place for that graph. I'll just undo that. Okay. I wanted to see if I can drop the graph off in this spot here. So if you have questions about this one, come ask me. But if you're watching this video, then don't have any questions. Never mind. Never mind. This one here is just using identities, trying to figure out what values these end up being, because sometimes things just cancel straight out. If they cancel straight out, it leaves you with a number like 1, 0, 2, a half, or something. So we're going to pull out our, you can't see it right there. I'm going to pull out my formula sheet here. Got my identities on it. And yeah, okay, so I don't know what I was thinking about. And then we're just going to start replacing these things, and hopefully they work out. So I'm going to start off with a nice and easy one here. This is a nice one. So what I'm going to do with this one is I'm going to separate this a little bit. I'm going to have the cos theta over sine theta slightly different over here. Now remember, cos theta over sine theta is cotangent. All right, so this is tangent times, let me just go up here a little bit, times cotangent. Remember, cotangent is 1 over tan. So this is tan times 1 over tan. Cancels out, and leaves me with a 1. Okay, so I know 2 is equal to 1. Okay, so that's going to help me out here. My next one, maybe, let's see what the next one is going to be. I don't know, this tan squared one? Yeah, that's not too bad. Let's do that one. A couple of different ways you can change the tan squared, because I'm looking at my formula sheet. There's a tan squared and there's a secant squared there. Actually, if I rearrange that equation, so I'm going to take that equation that says 1 plus tan squared theta is equal to secant squared theta. Is there a way to rearrange that to make it look like what's inside the brackets here? So this piece right here, can I change it, make this look like that? So if I do this, I can minus over this piece and take the 1 and minus it that way. So I get tan squared theta minus secant squared theta, and that's going to be equal to negative 1. So this is equal to that. So what I can do now is I can replace this middle part with a negative 1 minus 1. My computer's dying on me. So it's a negative 2. Now, so far that's the lowest one. We've got negative 2, we got 1. This next one, hopefully somewhere in between or bigger or smaller. I don't know. We'll see. I got a lot of things here, so I'm going to deal with this quotient part here and see what happens. So I'm going to leave the secant alone. Let's leave that alone for now. I just want to see what happens if I try to do something with this one. So this would be 1 over sine, and cotangent is cos over sine. Remember, that's now what we could do is do times by the reciprocal here. So I'm going to just write it down here. So it'll be 1 over sine theta times sine over cos theta. Now, just like the tans, you can cross off the sines here. So I got secant minus 1 over cos. But remember, 1 over cos is secant, so this is secant minus secant, which is equal to 0. So my lowest value is that -2, so that's technically 1. All right. Now remember, you can never put negatives in these numeric response spots, so that's kind of helping you out. So I accidentally put in -2 in there. My next lowest value is 0, so that's 3. This is the second graph here, and then the highest value is equation 2. Is that right? Yeah, it is right. Okay. Non-permissible values. All right, so to figure out non-permissive values, we got to look at denominators, right? I don't see any denominators here at this point, but remember, they're kind of hidden away. These reciprocals and these cotangents and tans, they all have their own denominators. So, like secant, or cosecant, sorry, is 1 over sine. That's that piece. Tan is sine over cos. Secant is 1 over cos, right? Now, I'm not trying to prove this. You can see right now, like, just cross out the signs. They do equal each other. Yay, it is an identity. But I just had to worry about the bottoms. I'm not going to cross them off because the bottoms, before they cross off, are still included in my non-permissible values. So I have this one, and I have this one to deal with, right? So let's do the sine one first. So sine x cannot be 0. Okay. So where is sine x not equal to, where is it actually equal to 0? So I want to figure out what x cannot be. So sine, remember this is the y values. So where are my y values equal to 0? So it looks like my y values are equal to 0 here and here, right? So those two spots at 1, 0 and -1, 0. So everything's in radians over here, so let's just deal with radians. So it's 0, pi, 2 pi, etc., etc., etc. Okay, but now I've got to figure out the other one. So the other one says for cos, I don't want that to be 0. I'm going to draw this one out too. So where can that happen? So this happens when the x values are equal to 0. So this is straight up and straight down. So pi over 2, 3 pi over 2, etc., etc., etc. Now you notice they only give us one general solution over here, so we've got to think, is there a pattern? If I put these both together, can I create a pattern? So these two things together, if I were to write them on one set of axes, I have 0, 90, 180, and 270. So I can see there's a common difference here of pi over 2 all the way around. Right, before it was pi, pi, pi. So I'm looking for the one that has the pi over 2n in it. So the only one that actually has the pi over 2n in it is this one here. So there's my answer. Yeah, looking pretty good. Okay. Oh, now we're into the perms and com stuff. Ooh, yay! And there's a composition stuff at the end here. I'm going to do the written response ones, just because I want to explain something about the sketching one, which I might talk about in class tomorrow as well. Oh, did my wife talk to me yet? Oh, man. Oh, she's not happy. Is she happy? She's sending me GIFs right now. No. Yeah, it's a bit late. You can see now it's like, rather than it was 4:20. I know it was a bad time to start this thing. Now it's 1:40 or 5:44. But we're on a good time. Look on the side there. It's been an hour and a half for a 2-hour exam. We're almost finished. So we have a 9-person volleyball team trying to stand in line, and they want to play the shortest player on one of the ends. Doesn't mention which one, and the tallest player in the middle. So we have 9 people. So I'm going to use the fundamental counting principle here, because we're talking about arrangements. I know it doesn't mention that, but photos are always arrangements. 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay, so we could put the tallest person in the middle. That's what it says here. Right? I want to put the tallest person there, and the shorter person here, or here, right? One of those two orientations, because it didn't mention which end he's going to have to be in. And that orientation is different. I don't know which position is better, but it is different. So for the first one, we only have one choice for this one, and we only have one choice for that one. Same thing with this. We only have one choice, and then we have a choice. And then after we're finished those two, because the 9 volleyball players include the shorter person, we have to take out the 2. There's only 7 spots anyway, so there's going to be 7 for what's left over, and then, because I'm not allowed to repeat, right? And then the next person, because I can't use that person again, I got to go 6, and then 5, then 4, then 3, then 2, and 1. And this one's going to be the same thing. I got 7 choices for that guy. And then because I'm not allowed to repeat, I have to decrease by 1 each time. Now mathematically, that's just 7 factorial. Because 7 factorial times 1. So 7 factorial, but 2 of them is 10,080. Yeah, that is right. 10,080. So you have to be very careful about some of the wording, like this one. It's one of the ends. It didn't specify which one, so you have to think of both situations. So a nice little OR situation. Remember, OR means plus. I don't even know what happens if you multiply them. You're not going to get the right number. Okay. We got polygons, 4-sided polygons. To draw a 4-sided polygon, you just need 4 sides. So I can choose any 4 sides here. It doesn't matter what order. I can only draw one 4-sided polygon there. But polygons don't have crosses. So there's only one way to draw a polygon here. But you just need to pick 4 sides. It's not too bad. This is just going to be, because there's 6 dots, we have 6 things. And because order doesn't matter, you just need the 4 dots, you just put lines on them, got a polygon. Just like a handshake, just like a triangle. It's going to be 6C4. Okay? But it says at most 4 sides. So this is just the 4-sided one. We're going to get to that point in a second. So that's 15. But I can't go any more than that. But at most means that's the maximum number. So that means I can have, or I can create triangles. Or I can create, I don't know. It says polygon has 3 or more sides, so I can't, I don't know what I'm talking about. Or I can create triangles. It's like a single line is not a polygon. It's got to have at least 3 sides. An internal piece. 6C3 is 20. No, it's eraser. Add them together. 35. Cool. Okay. Now, oh, this is a nice one. The 9th term in the exponent. So we're trying to find T9, but remember, the formula says K plus 1. Because of this, we want this to end up being 9. Our K value is 8. Okay, so now we know our K value is 8. I go to the formula. So 10, because it's N, CK. So we decided to put that there. Bracket, bracket, 3x to the power of n minus k. So I'll go 10 minus 8 here, to the power 2, bracket, bracket, -1 to the power of k. Now these negative values here are to throw us off, because if you take a negative number raised to an even number, it should always be positive. So term 9 is going to be 10c8, 45. This is going to be 3x to the power 2. I didn't simplify that down yet. This is going to be just +1. Okay, so it's going to be 45 times 9x squared, because you have to square both those pieces, times 1. And what is 45 times 9? Times 1. It's 405. 405x squared. We're just looking for the coefficient. Right? Coefficient is just the number that's in front of the x's, or whatever other variables happen to be there. Cool. We necessarily threw like a -4 or 5 in there, just to really kick it to those ones that can't square a number properly or raise it to the power of 8. That was all I had to do. I don't know why I'm looking at that one so much. Okay. Okay, how many terms in expansion? Remember when we did this, if I go back to this previous one, there are 11 terms in this one. It's always one more than the exponent, right? So if my exponent is n, that means there has to be n plus 1 terms, right? So I could cross off pretty much this one and this one. So we're just looking for the correct ones, right? So number 3, cross off, right? So that's the only one that works for the number terms. Now the largest exponent on the variable is blah. It's an interesting one, but what it means, if they were to do the expansion of all n plus 1 terms, which of those n plus 1 terms is going to have the biggest x to the power of, the biggest exponent on the x? So, based on what our knowledge, we're just using some logic, because this has the larger exponent, I should probably use some different color here, because this has the larger exponent versus the one below it. It means that the closer to the beginning, the bigger the exponents would be. That's actually probably going to be the first one. So the first term, which is going to be T1, which is going to be NC0, is going to be x squared to the power of n minus 0, -1 over 2x to the 0. Now, why this is important, because if I have exponents in the denominator, they start subtracting out exponents, right? I don't want that. I want to make sure my exponent on the top stays as big as possible. So we want this to kind of cancel out. So anything raised to the power of 0 is 1. NC0 is also 1. So this one here is going to be x to the 2n. So the biggest exponent I'm going to have is this exponent right here, which is this one here. So it'd be 3, 4. Or 4, 3, because order doesn't matter. Okay. Now, what was I looking for? I don't know anymore. Yeah. Determine which function has a larger value. X is equal to 0. Oh yeah, yes, this is okay. This one just asks us to show most of the work. So I'm actually going to do this one. I'm going to go through my steps of what I would do to solve this. So J is the composition. Okay? So J of X is the composition. So I'm going to write it out. But I'm going to write it out the way that I like a little bit more. So when I write this, I write it out this way. F of G of X. Okay? But I want to find out when X is equal to 0. So I actually want to find J of 0. So I actually want to find F of G of 0. I think I said j up there before. Okay, so what this means, how I usually do this, and I do it all the time, is work from the inside out. So my first goal is to find out what g of 0 is. I want to find this piece first. So I'm going to look at g when x is equal to 0, and I notice it's -3. Okay, so I'm going to take this, and I realize that this is -3. So I'm just going to highlight that. So that's right there, right? That's -3, right? You know, watch out for that scale. Okay, and then what I'm going to do is I'm going to take that at -3. Then I'm going to look for f of -3 now, because now my x has changed. I'm going to use -3 as my x, so that's going to be right there. So my f is actually +1. Okay. Now I want to determine which is the larger value, so I'm going to do the other one. So k is the division of the two things. So k, I'm going to write it out first, is f divided by g. But I want to find k of 0, so I'm going to find f of 0 divided by g of 0. Now I found g of 0 already, so g of 0 was -3, but what is f of 0? F of 0, I'm just going to highlight that one again. Right, and then f of 0 is right here. When the x value is 0, that's -2. So -2. So this ends up being, as a decimal, approximately +0.67. So therefore, j of 0 is greater than k of 0. Actually, I'm going to write this a little bit differently. J of x is greater than k of x when x is equal to 0. Well, yeah, that's what I think the answer is. I hope that's the right answer. Let me just double check. We can just scroll down here until we find the right answer. Hey, look at that. There's a larger value. So we found that out. Good. Let's go back up here. Let's try the next one. Okay, so now we're going to have to try to sketch this graph. Now, what's very key about sketching this graph is we want to figure out, we want very specific characteristics. We want to make sure the domain is right, the proper range. We've got the min and the max values in the right spot. Like, is there going to be a new a min and a max, right? Now, this is h, right? Yeah, this is h of x. When we multiply linear lines out, we get a new quadratic. If we add or subtract linear lines, we get a linear line. If I add or subtract a quadratics together, we probably get quadratics, unless the quadratics just happen to line up and the x squareds kind of cancel each other out. But these ones don't look like they really line up. But maybe they do, right? We just have to make sure when we go through this, but it looks like they're slightly off from each other, so it looks like they don't line up. Plus also a minus seeing 1 from the other. So I'm going to get a quadratic here, because one's a negative, one's a positive, so it looks like it's going to be quadratic. Okay. So there's lots of things down here. Coordinates of the y-intercept, the domain as well. I want to know what that is. So let's start with the y-intercept. So I'm going to minus g. I'm going to have to scroll up and down here quite a bit. So g minus f. So -3. So remember, this is going to be y minus y. That's what we're doing. Y minus the y values. So when x is equal to 0, I'm going to go -3 minus a -2. So I get -1. Okay? Let's go down here, put a -1 here. So according to the x and y, so 0, -1. Okay. Okay. And then you notice that there's nothing else is going to be to the right of that because g is undefined to the right of that point. So I'm not going to draw anything over there. This is where my graph stops. The dot as well, so it's solid. So it's a solid dot there. Then I'm going to go in another dot in because I can calculate that one. So we got g, which is -4, minus f, which is 1. So that's a -5. That's nice that they give us enough. So this is at -1, right? Or yeah, -1. X is equal to -1. I got negative 5, so a dot right about there. Okay. Now when x is equal to 2, or negative 2, sorry, I've got negative 3 again, minus 2. Now this one's misleading because now I've got another negative 5, right? But what's misleading about this is that this is not a flat line. You're going to see later on that somewhere in between that is there's a minimum value. But let's go to the next point over. So negative 3, so it'd be 0, that's the y value, minus 1. So I got negative 1. Right there. Oh, it's looking symmetrical, like it's a quadratic. I assume that's going to be a quadratic, because a quadratic is a quadratic. And then g here, the last point I can do, because there's nothing to the left of negative 4. So I'm going to have to stop at negative 4. So I've got negative 4 here. So this would be a 5 minus negative 2. So positive 7. Way up here. So the graph stops there, right? So there's nothing there on either side. So I can actually do the domain here. So x is in between negative 4 and 0, including those points, because they are solid dots, x, e, r. Okay. Now, for the next part, I want to just make sure, because I know it's going to be a curve, because if subtracting 2, this is definitely not a straight line here. If it was a straight line, obviously the dots would all be straight. So I want to make sure I have the proper minimum value. So at like negative 1.5, I'm going to go back up here to negative 1.5. So right about here and right about here, I'm going to minus these two values and just make sure it's not negative 5. So that point down there in G is like negative 3 point, I don't know, let's say negative 3.6 or so. Okay, and then minus the 1 point, I don't know what that would be as well, 1.6 or so? It's like negative 5.2, so it is less than 5. So there is a min value somewhere in this point here. Somewhere here there's a new min. So that's very important for the markers. They want to know, can you identify, is there an actual min somewhere else? It's not just a flat line, and this is not just going to be a straight line. It's not going to be just straight, right? It's going to be a quadratic. So it's going to be curved here. And that's a really poor curve, right? So I don't think they're really marking us too much on their how well you can draw this. But you know what? I'm just going to make sure that the markers know this is curved. It's quadratic, probably quadratic. All right, there it is. So, but then there's a min value here somewhere between these two values. I don't know exactly where. It's not the best. I can't really draw this in the best way. But stops here, begins there. We got that. Let's see what they say. Yeah, min value somewhere about there. They don't mention it here. Set notation or this. Is an ordered pair because it says it's a point for 4 marks. Yeah, cool. Okay, let's see what the next one says. I think, yeah, so let's solve this one. State your solution says exact value, so that's pretty important here. So I don't want decimals. I'm going to put them in radians. So there are going to be some pies in here. But we're going to solve this one. Almost at 2 hours, so I'm on track. I've got a lot of talking here, so. Now the thing about this is it's a quadratic, so I'm going to make this equal to 0. And I know it's a quadratic because of this square here. So I'm going to create over here a nice little let statement. So secant theta is equal to A. And I'm going to actually solve this equation to start off with. So I'm going to factor this out. 2 and 1, positive 2, negative 1. Cool. So A is, because this is not a non-permissible question, these are the actual answers. It's not in the denominator or anything. There are non-permissible values. We should worry about those. So where was I just want to make sure that I have the proper non-permissible values here. Because that can be part of this. It's 3 marks long. So let's see. So 1 secant is the same thing as 1 over cos. So therefore, cos cannot be 0. We solved this already. That means theta cannot be. So this would be straight up and straight down. Just in case, I just want to make sure that the answers I get don't match up within these non-permissible values. So we got a straight up 90 degrees, so that's pi over 2. I have no idea why I thought so long about that one. Dot, 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 dot. So if I end up with any of those answers, I could probably should cross them off. Okay, so that's just a side note. These are my non-permissible values. Now, the markers want us to kind of be organized a little bit. I don't really like where I put that. I'm just going to put that on the side there. I'm not going to continue on to the question here. So A can be either -2 or it can be 1. But remember that A is secant theta. So secant theta can either be -2 or +1. Okay. Now remember, secant theta is also equal to cosine. So where is cosine equal to -1/2? Remember, that's going to flip that over. All right. And where's cosine equal to 1? Okay, so right now, it doesn't match any of my non-permissible values, so that's good. We just have to solve these two pieces now. So for the -1/2 section, cosine is negative, very key here, negative in not the first quadrant and not the fourth quadrant, but it's negative in this quadrant over here. Right about there. And this quadrant down here. Okay. So that's where it's negative. So I'm looking for these two solutions. Something in the second quadrant and something in the third quadrant. Now to solve this, I'm going to do my reference angle. So you can do the reference angle two ways. Remember, you can do cos inverse 1/2, got rid of the negative, and I think it's 60 degrees based on our unit circle. Yep, 60 degrees. Now, you could do your math whatever you want, right? As long as you answer in the units that they specify. So the domain here says it's in radians. Make sure you do it in radians after the end. But you can put 60 degrees, do all the work at 60 degrees. But I'm just going to write down pi over 3. Okay. Cool. Now, once I know that, my two answers here, so let's put down 60 degrees here. My two answers are going to be 60 degrees, so one is going to be, what am I supposed to do? This is supposed to be from 2 pi to 3 pi. So I'm just going to do the first one, then I'll deal with the domain later. So my first answer is going to be 180 minus 60. What's 180 minus 60? That's 120, right? So that's 180 minus 60. So that is 2 pi over 3. But this is not my answer, right? This is just within the first domain, so we're going to have to write out something later on. Okay, and I don't know why, this was, I'm getting a little tired, I think. It's just going to take a little bit of time here. So 4 pi over 3. So this is 180 plus 60. Okay, so now we know our two angles. Okay, awesome. But they don't fit within our domain. So we're going to look for coterminal angles that fit within this 2 pi, which is 360 to 3 pi. Which is 540. I just put 180 in those two spots. So my angle's got to fit in that spot. These ones don't fit there. Right? This is like 240 and this is 120. So I just want to make sure I can find coterminal angles that fit within the right spots. So let's see. So coterminal angle. I'm going to take the 120 that we had and add 360. If I add 360, 120 plus 360, I get 480, and 480 fits within there. So that's going to be one of my answers. So a coterminal angle, I'm going to add 2 pi to this, add 360. Is going to be 8 pi over 3. So that one fits. And then if I do the same thing for the other one, 600 degrees, and 600 degrees is too far, right? So I'm going to write that out. Just 1 second. So this is going to be 10 pi over 3. But I'm going to cross that one off. Okay? Maybe I'll just justify it. Too large. Okay. Too large. And these ones up here, I'm going to cross those ones off because they are too small. Okay. But there's one just right here so far. Okay, so we're doing a pretty long way to do this. I'm going to go to the next one here. Draw this out. Where's cos equal to positive 1? There's one angle that does that. Right there. 1, 0. Just positive 1, not negative 1. Positive 1. So there's only one spot for that. So my theta for this one will be, if I were to go through this, is 0, 2 pi, 4 pi, dot, 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 dot. Now, which of these fit? You have to be very careful. Oh, there's equal signs here, so 2 pi fits. So I'm going to cross that one off, that one off. This one fits just fine. Now, just to organize my thoughts, I'm going to go down here and write out my 2 angles that work. Perfect. I just want to see that work. Is that the answers there? There's a lot of work here. Okay, what did they do here? Accurately sketch. You might want to read through this. I'll have to read through that too. Yeah, look at that. 2 pi, 8 pi over 3. Perfect. Now, they did all their work in radians. I just want to see what they did here. Use an algebraic process to determine the correct solution in radians. So if you found the answer in degrees, they would have gave you 2.5, right? If you found your answers in radians, but they were incorrect, they would have gave you 2. But if you answered your question in radians, it doesn't specify anywhere in here that you have to use degrees to do the whole question. Or outside the domain, 2.5. Yeah, okay. Not bad. Okay. Let's go back here. So just make sure you answer in the proper units. I'll just put a box around this answer here. I'm happy. Okay, cool. General solutions. You guys know how to do general solutions. If you look at the answers, the word state just means just give an answer, right? Don't bother. You don't have to necessarily show the work to do this. Like I said, there are 2 correct answers. You can just pick every single angle there. Remember, our general solutions, you always use the principal angle to do that. So they might have a bunch of angles here, but you should always be using the principal angle, right? These positive angles here, all right? So B is technically, what should these be in theta? Theta, okay? B is theta is equal to the principal angle, pi, plus 2 pi n EI, right? So that's B. Now A and C can be connected together. You don't necessarily have to, You could just write them out separately. Like this one here is going to be 3 pi, so it's 135 because it's 45 degrees. I think it's 3 pi over 4, right? Yep, 3 pi over 4. So you can go 3 pi over 4 plus 2 pi n ei. That's for A, right? And C, you can say that this is 5 pi over 4. 315, right? Because it's 45 less than 360. And that is 7 pi over 4, my bad. So 7 pi over 4. So I'm not going to use negative pi over 4. I'm going to use the principal angle, the positive angle. Now this is fine. Or I can connect A and C together as 1. Because there is a pattern between the two where you're adding pi instead. There's only a pi difference between 180 degrees between them and ei, right? So it's up to you how you write that, but the B there has to be kind of separate because there's no pattern for him. This one here, algebraically determine handshakes. I might as well just do this. This one you can read through the example here, and there's the answer for that. Just for completion's sake, let's answer this question. Now remember, when you're handshaking or passing messages, it doesn't matter who initiates it. They're just creating encoded messages with each other, and they're just passing them. And they just talk about different pairs of students. So, but the problem is we don't know how many students there are, but we know there's 630 pairs. So I know that I have a number of students, and to create a pair, I need 2 of them. And I know that there's going to be 630 because I'm not too concerned about order at this point. So, using our formula, we're going to go n factorial. So this is, they're expecting, because it's algebraically determined, they're expecting all the steps. Don't skip anywhere. When you do the expansion, write it out. When you cross something out, cross it off, and then maybe show it again afterwards as a simplified form. Don't skip anywhere. All right? N minus 2. So 630. Okay. And then here, I probably, okay, so can't cross anything off, so I'll start expanding it out. And then I'm going to show it there before I cross it off. Some people just like to not show that part. But show this before you cross it off, right? Don't just write n times n minus 1. In this step, I'm actually going to write n times n minus 1 is equal to 630. So I'm showing all my steps. I'm going to multiply this in, because you don't have to show the little rainbow there if you don't want to. And I'm going to make it equal to 0. And I'm going to show the factoring. And someone's at my door. I don't know who that is. Yeah, I'm still here. I'm always working. Working hard. I'm actually making a video for my students. Going over my diploma questions. Yeah. Is it nice? I don't know. Oh yeah, that's always fun to do. Yay! It is fun, yeah. I can't seem to find any factors for this. Why is that possible? You probably already found them, huh? Let's see what we have here. We got 30. 30 doesn't work. 25. 25 doesn't work. 23. Definitely not 23. Why am I having trouble finding the factors? I'm using my dinky calculator here, so it's taking me a little bit of time here. 35? No, 35 is going the wrong way. 22? No. 24? No. 26? No. 27? Why am I having trouble? Did I mess up with my... Oh, you know what I messed up on? Yeah. So it's a good thing. I couldn't find it. I couldn't factor it. I forgot about this guy. There's a little thing here. 2 factorial here. There should be a 2 factorial here. All right, so this is still divided by 2 factorial, right? Then I could times that 2 factorial up to the other side. And then maybe I'll erase this. Good thing I couldn't factor. Couldn't find the answer. Hopefully you guys caught that. 630 times 2. Number's going to get bigger, but it should be factorable at least. So n squared minus n minus 1260. Now it's equal to 0. Now I can factor this. I don't know what that is. Let's see, 200? No, it's definitely 200. What is it, 50? No. Why did I even guess 50? No. Guess 30. Oh, they're 35. Okay, so I know 35 and 36. They're one apart from each other. So n minus 36 and n plus 35. I want to add to a negative number. Then I look at that and I say n is equal to 36 or negative 35. But in the context of this question, cannot have a negative number of students. I'm writing that down. You guys, when I write it down and it says determine up here, you need to write this stuff down. You have to justify why you did something. Why did you cross that off? So you have to justify that piece. Right? The other 36 here, I'm going to go over to my verification side. I'm going to verify it first. Verify. Just make sure it works. So I'm going to go 35C2, and that's equal to 635, or 630. Check mark. So this answer is right. There's 36 students in this classroom. I'm going to write that down. So there are 36 students in the class room. You know, I actually didn't verify it. I should actually do it. I just said I did, but 36. Because that's the problem. I used 35 rather than 36. So it would be 36 here. C2. 36. C2. Ah, there we go. 630. Type to my calculator. Use 36. 36 students in the classroom. Okay, I'm done. All right, I'm going to go home. Have some dinner. Okay, I'm going to stop this.